No? Yeah. Okay. All right. Is it anyone kind of tired right now? Is that what it is? Yeah. I guess it's always like their first class in the morning. So I do apologize. It's kind of rough on you guys. Why are you up so early? Oh, okay. What is it? Oh, cool. Oh, you are super dedicated then. Yeah. But we got a lot of respect for that. It's not easy. Uh huh.
Now we're doing the document.
That sounds awesome. Yeah. Well, it sounds tough. Sounds like a lot of stuff. All right, guys. No warm up today, but we're gonna get into the first example problem pretty quick. So I'm gonna let's see, 4.2. Oh, you know what? I think I jumped ahead. We're not gonna do 4.4. We're gonna do 4.2 first. So my apologies. We're going to do 4-2 first. We will come back to 4.4, but we're going to do 4-2 implicit differentiation. So we won't jump into an example problem right away. Implicit differentiation. So our first note is we're going to learn this weird technique. The first few notes that you're going to take, you're kind of going to wonder, why is this beneficial? Why are we learning this? Because it seems like it's extra work and extra steps to solve these type of problems, okay? And then afterwards, I'm going to show you a problem where it is beneficial. But you're just going to have to take my word for it. For the first few notes, you're going to write this down. You're going to be like, I don't see why we're having to do it this way, okay? And then when you do the example problem, hopefully you'll see that it is helpful. So first, let's define what is explicit differentiation. Like, what does explicit even mean as opposed to implicit? And an example would be this. Y is equal to 3x squared minus sine of 7x plus 5, ... And then I'm going to ask you for dy over dx. We can actually make this a warm-up problem. So let's go ahead and do that really quick. Try to solve for dy over dx, and maybe get up right now and don't get too comfortable. Get up right now and find a whiteboard space, and then try to find out the derivative of this. So all I could say is take care of these components separately. 3x squared, find just the derivative of that, and then deal with this guy next, okay? So try your best to remember what you can about derivatives. If you need help, I gave you a handout. You should have grabbed this near Emily. It's like in front of Emily's desk. It's a list of all the derivatives we're going to need to know for the whole year, okay? So if you don't remember the derivative of sine, look at your handout. It's a little hard to see, but try your best with it. I don't know. Do your best right now. I'll find you a better sheet later, hopefully during the year. Okay. Good luck. Okay. And talk, right? Warm your brains up. Okay. We don't want to just be like passive melons here, right? Just enjoy yourself. Now I'll turn on the lights. I'm going to freeze frame this. No sign-in sheet. Just grab a chair and grab a handout, okay? Hello, Gleta. Go ahead and grab the handout, and then just work together. on this weird problem that we got. Sean, same goes for you. I have a warm-up problem right here to solve this derivative. The whole point is
I remember thinking it, and I was like, "This is just it's so complicated."
if you think you're good with your final answer, go ahead and have a seat, and then we'll kind of review what the most common mistake is. You take a look at other people's too. You kind of compare yourself and your work to each other and see if you're happy with it, what other people are thinking. Anybody want me to turn on the heater? Yeah, you don't care. It's at 72 degrees, so it's like over 10 bodies in the room. Alright, I guess so relax, I guess. Alright, I'm gonna unfreeze the frame and then you guys are gonna see the solution and then you guys can kind of compare your answer to mine. Yeah. Okay. So just quietly compare your answer to what I have up here. And if you made a mistake, it's cool. What do you think is the most common mistake? Let's say if this is a multiple choice answer, and this was like only one of the answers you could select. They're gonna try to nail you with this, with the common problem here. What do you think is a very common mistake here made? Think about it. Does anybody have an idea of where we make the most common mistake? Well, I think you guys understand if it's a plus or minus and they're not being multiplied, you just take the derivative of each guy by itself, right? I think most people get that. So we use the power rule to solve for this. Without looking at my work, can you just do that in your head? What is the derivative of 3x squared? What should that be? What's it?
6.
Yeah, it's just 6x to the first power. Does anybody remember what the derivative of sine of anything that's in there? Like, what is the derivative of sine of whatever it is that you put into sine? Cosine. So that's no problem. The most common mistake, though, is something that we didn't really get to, and I made a video for last week. Go ahead and say that again. Okay, what does that mean? If you can explain it just like in basic terms where maybe everyone can kind of understand if you're...
Basically, you do the derivative of the outside, like
Okay.
the sine of x, and then the sine, and then you just leave whatever that is in, and then you times it by the derivative of the inside.
Got it. Okay, so that's the most common mistake. You got to be really attentive to one detail. We all know that the sine, like the derivative of the sine of, kind of pay attention to the way I'm emphasizing this, the derivative of sine of whatever is in there as the input is cosine, and then you leave the input the same way. But ask this about, like, to yourself, can you actually take the derivative of 7x plus 5? If you can, we do what's called a chain rule. And the best way to describe it is there's sort of like an outer function, the sine of whatever's in there. You could take the derivative of that. But whatever's on the inside, if you could take the derivative of it, take it. So here's what it's going to look like. It's a chain of commands, right? Or a chain of procedures. You first take the derivative of the outside, which is the cosine of whatever's in there. You keep it the same. And then you take the derivative of the inside, 7x plus 5. I can do that in my head. The constant is like plus 5. So the derivative of a constant is 0. And then what's the derivative of 7x? Like, it's just 7. So what you do with that 7 is you don't add it, you don't subtract it, you don't divide it, you multiply it, okay, to the derivative of the outer function, okay? So the derivative of the outer function is cosine of whatever was in there originally, and then you multiply it to the derivative of the inside, which is 7, okay? So very common mistake. Again, on a multiple choice problem, one of your choices would be this. 6x minus cosine of 7x plus 5. And I would say that's 50-50. 50% of people in haste would select this answer. The other 50%, okay, if they did like not a little bit more studying, but during their studying, they just happen to see that, oh yeah, I think I would make that mistake. That's the difference between one question you got right and one question you got wrong in the exam, okay? I hate to be so binary, like, you know, you got to know it or else you're not going to pass, okay? It's just try your best, right? So that's just one thing that you can try to get down, right? Before the exam. All right. That is what we call... So the whole point of this is to talk about what is explicit differentiation. I'm going to say here, and I'm going to make a comment that the derivative of y is explicitly written out here. Here. Sorry, the derivative of y is explicitly written out here, like out here. That's what I meant, like right here, in terms of x, like purely x. This is purely a derivative of y that is all in terms of x. This is indeed dy with respect to x. It's all laid out. There's no hidden meaning, okay? Slowly, we're going to transition. I'm going to move this up to what's called implicit differentiation, where there is implicit meaning in what you're taking the derivative of. So, differentiating implicitly. And what is this going to look like? An example of this, you would have to find dy with respect to x, let's say, if y squared is equal to x. So now we're going to start getting into the territory of equations where y is being played around with. Before, it was very explicit what y was equal to and what y alone was equal to. Now, funky things are going to be starting to happen with two variables. And that's where we need to start gravitating towards a slightly different technique of taking derivatives, okay? Before, y was just very simple. Y is equal to 3x squared, blah, 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 everything in terms of x. Now, though, this is a new field where y is being toyed with and x sometimes is being toyed with. We have two variables that are being messed with, and you still have to take dy with respect to x. It might not seem like anything crazy, but when you try it on your own with what you already know now, it's just not enough, okay? That's why you're here at class, and that's why there's a completely different section to explain this weird phenomena of what to do in this weird situation. Okay, so how you would solve for this, the solution to this would be pretty simple. So I'll say answer, or you can write solution to this. It's not too bad. You just take dy of dx. You guys never really write this step down. But formally, I'm sorry, it should be, sorry, it's a, let me shoot, I'm all out, wide out. Just say d over dx. sorry, d, that's just d over dx, and this is d over dx. And I'm putting that in parentheses. This is an operation. You're taking the derivative of whatever's in the parentheses. Before, you would kind of leave y by itself, and then you would just change it to dy over dx. You wouldn't do anything much with it. Now you literally have to take the derivative of y. But it's not that scary. What is the derivative of any variable to the second power? Don't be scared, just... Yeah, it'd be 2y. Here's where the implicit thing comes into play. I'm taking everything in terms of x with that variable. We don't actually know if inside of y is a weird equation with x. So like meaning this, everything's in terms of x, y squared. For all I know, inside y could be a completely different equation that has x in it, like x squared plus 2x. It doesn't explicitly say. The way it's written before, I explicitly told you what y is equal to, right? Here, implicit means there's kind of hidden meaning. I don't actually know what y is equal to. So it's a weird kind of chain rule. Conceptually, a lot of people just look at this as something that they have to memorize in implicit differentiation. After I take the derivative of y squared, I have to write times dy over dx. Okay. The reason why, though, is because you have to look at it like this. The outside function is y squared. It's something being squared, and then you take the derivative of it. The inside function is y, but we don't know what y looks like. We don't know if y is equal to y x squared plus 2x. It could be y is equal to 3x to the 9th power plus 7x. I don't know. It's not explicitly told. So how you compensate for that is you have to say times, like a chain rule, the derivative of y with respect to x. That's all I got, okay? That's all I see. I just know implicitly there could be a weird equation inside that. Does that kind of make sense? So for now, all it's going to mean to you guys is I guess I just have to take the derivative of both of these guys, and then I have to add that times dy over dx part, okay? But really study what I'm saying and try to make sense of it, right? It's kind of weird hearing it for the first time. Okay, if you're taking the derivative of x with respect to x, what's the derivative of x going to be? Yeah, just 1. That's all. The name of the game is just to find dy over dx. Look at it like an algebra problem. I'm finding a lone variable called dy over dx. So what I have here is 2y times dy over dx is equal to 1. How do you isolate this to become just dy over dx is equal to something? How do I solve for dy over dx? Divided by what? Yeah.
dy over dx is like another variable.
Kind of look over that and see if that kind of looks familiar, like this sort of math. It's just algebra.
With a weird thing.
It's a weird way of applying algebra. I think this is what makes calculus so hard. You use math that you learned up to this point for conceptually really hard things to understand. For once, you might want to actually learn why you're doing these things. This is what makes calculus, I think, really tough. Okay? So dy over dx is now equal to 1 over 2y. How is this different than something that we had before? I'm not asking for anything crazy. Just look between this answer and this answer. What's really the big difference here in these two derivatives? Hey, Mr. Zapala. Good morning. Anybody see any big differences between this guy and this guy up here?
Like for one, there's a design, like a function, and there's a y in it.
Namely, the fact that there's a y in your derivative. We're very explicit about everything being an x. For all I know, like I said, y could be inside of y could be an equation. Like y could actually be equal to, it is actually some kind of equation with x in it. I'm not going to explicitly say what it is because I don't know it. So we have to leave it in this way, okay? I'm going to give you a very challenging problem that I want you to try out. If I gave you y squared is equal to x minus 1 over x plus 5, and I asked you to find the derivative.
You both said 5, but you put +1 on the bottom.
I'm sorry, what?
When you, you said +5, right?
Oh, did I? Yeah, I didn't. I totally didn't mean to. So your basic thing that you're going to do is just try to isolate dy over dx by itself. I'm not going to say you guys might get this right or wrong, or I'm not going to say you're going to get it right, guaranteed. But I want everybody to go up on the board and give it a shot, okay? If you're not comfortable, I would totally find someone to link with and work with. If you're not comfortable, find someone that seems like they know what they're doing, but that can help you out to understand. And then, yeah, let's work. Let's freeze frame this for a second here. Sean, could you turn on the light for everybody so they can work? I don't think this is really easy. I think this is a pretty tough problem. Did you figure it out, Sean?
I mean, we're going to amplify put d instead of dy over ds, like in capital D, for most of the work, so I didn't have to write it out dy over dx. I put it like in the end, but
That's really clever.
Because I didn't really, because that's what it is. But still, putting that. I thought once I mentioned one, write it out.
You know what's funny is when we went to college, a lot of the textbooks and higher level physics they love really long. So they do that all the time. Where they say, a little note, we're gonna say that that's like they use it for alphabet. So it's like dy over dx is equal to like theta. What? And then the whole time you see theta is equal to that. And at the very last minute they exchange back that root symbol, what the notation is to do with everything. And then most students they'll see that initial note and they can't remember the right. The fact that you're doing it now because you see it's you're actually, I think it's going to help you better. It's not going to be as daunting of a task for you to understand how to conveniently do something like this. So really good. Actually, I'm going to commend you for doing that. That's actually really good.
The girl looks like.
Yeah. Fast, right? Yeah. So that's actually really cool. Yeah. I'm actually going to bring that up. That's actually really good. Really good. All right, so I'll say if you got 1 over y times x plus 1 squared, you have done your problem correctly. In fact, you can write down, I would suggest you write down the work that you did if you got that answer correct as your notes. So take a few minutes to rewrite what you did on the board in your notes. Now, if you got, let me show you the answer. Oh, sorry, Emily. I'm gonna ask you to be a door person. I'm gonna take turns at that whole table for you guys to. Because I don't want to make you that sole person just because you by default sat closer to the door. All right. So you don't have to write down my notes because your work is perfectly fine. I want to kind of stress to you guys that if you guys did something a little bit differently from me, as long as you got to the quote unquote right answer, it's perfectly fine. Okay. That's how math should be. You approach it from different ways. I think for the most part, we did it similarly. You guys took the derivative of both sides with respect to x. You did the product rule, which I know everyone's a fan of. Okay, when you see it, I think if you did everything correctly, you should get to a point where you have 2y times dy over dx is equal to this beautiful mess over here, right? Let's see. And the end, I think a lot of you guys did a really impressive job in remembering that we're solving for just dy over dx. So we divided both sides by 2y. And then that actually kind of, this 2 up here and this 2y below here, it's like 2, it now becomes 2 divided by 2y times x plus 1 squared. We realize that the 2 are similar factors, so we just kind of factor them both out of the numerator and denominator. And you have a final answer of 1 divided by y times x plus 1 squared. Implicitly, y could be some kind of equation that is equal to x, okay? That in some way or form has x in it, but we don't know. That is implicit, okay? That's the part that is implicit. What else was I going to say? Okay, one more thing too. Stephanie brought up something that I think I should share with you guys in the future. To save, I'm not suggesting you guys have to do this because it makes your work more, it can make it more complicated or complex for you to follow. For my brain, I couldn't do this, but I wish I tried to do this when I was younger. She realized that she didn't want to keep rewriting dy over dx is equal to dy over dx is equal to over and over again. So what she did was she condensed it down and just made it another variable. You can do that. You can just name it another variable like capital letter D. So every time dy over dx, like where I have dy over dx in my notes, she just replaced it with d, like capital D. And at the very end, where she solved for capital D, she rewrote it back as what she equated it to, which was dy over dx. That's not a trivial fact. That's not something random I just said was pretty cool. The reason why I say this is when you guys go to college and you guys plan to take more higher level mathematics or science, in your textbooks, the authors have they have no regard for how the student sometimes understands an average fairly high level student understands the text at all, they sometimes without question just have something like that. They say, I don't want to type this up, so I'll just make it equal to. What's even better is they use like a Greek alphabet letter to make it even scarier looking, right? They'll just replace it with like gamma. Do any of you guys even know what gamma looks like?
Yes.
You might. I don't. Okay. They'll replace it with gamma, and then they'll just start going crazy with gamma. And then at the last minute, you're used to seeing this weird Greek alphabet sign. And at the last minute, or like the last sentence, they switch it back to like dy over dx. And you're like, what happened? I have no idea what I'm reading. Okay. Just keep in mind, they love doing substitution because they don't want to type things up. Okay. So this is not trivial. This is actually pretty cool. That Stephanie did it just out of her own convenience. She hates rewriting dy over dx. And in the future, when you read these textbooks, just keep in mind the people typing it are doing it late at night too, because that's their job. So they get really lazy, and then they're like, well, you know what? These kids should know if they're taking these classes. And they do that kind of stuff, okay? And it drives me insane, like as a student. So, but
I didn't put it on my notes. Man, I got tired of it.
yeah, right. So if you what I'm trying to say is if you want, you can do that just as an exercise. I don't know. You don't have to. It just makes it easier. Yeah, you can write less, right? I still don't. I can't. It just confuses me more if I try that. Okay, now, like I said, I kind of give you examples where you're like, I think I could have done this traditional way, like differentiating explicitly. I'm going to give you more and more examples where you can kind of see why differentiating implicitly is the way to go. And first, it's gonna be posed first as a challenge. And really, this isn't going to be found in the textbook, this note, but I call this section why we're differentiating implicitly. Why are we even doing it? Because you're going to be met with problems where it's just a lot easier to do it implicitly. So I'm going to write it in a way where you might see it posed to you as a question in the future. It might ask you to find the slope of a circle, x squared plus y squared is equal to 25 at the point, I'm sorry. Ooh, that's not good. My microphone just fell over, so give me a second to adjust that. I need to zoom out. Oh, it's still falling over. Oh, it's easier. Okay. All right. Can you guys all see that at the point 3 comma negative 4? Let's dissect this question first. When they ask find the slope, what are they really asking you to do if you're finding the slope? I mean, the good answer would be, well, just find the slope, right? But how do we find the slope? Yeah,
and then put the numbers in.
Oh, okay. Well, you took it the extra step. I was just asking about the first part because I think the first part is already kind of confusing enough because the derivative is a slope. It's asking you to take the derivative of this first, okay? And then they give you this point. Stephanie went the next step further and she said, okay, when you find the general derivative equation for this guy, afterwards, you just plug in the actual problem. Or no, plug in the actual point where x and y are, and you solve for it. So I'm just going to give you the option. You can either do it, so the old school way, explicit. This is the explicit derivative. No, differentiating. Versus implicit. Differentiating. You can just hyphen it if you want, like you can, or like you can shorten that down, this here. You can abbreviate it, not hyphen it. You can abbreviate it. See, obviously, guys, I didn't do very well in English when I was in high school. I did significantly better in math and science. And even at those two things, I wasn't the best at, but I was more comfortable, I'll say. So the older way of doing this, and I think you guys be like, yeah, why didn't we just do that the first time? Duh, right? The first way would be isolating y. You just subtract x from both sides, x squared from both sides, and then you have y squared is equal to 25 minus x squared. And then you take the square root of y.
And then you have to do it.
And then technically you have two equations. There is a reason why I'm making this very explicit, no pun intended, okay? I'm explicitly writing that it's plus or minus 25 minus x. And then you just solve for the derivative of both of these, right? For some of you that didn't see it before, you guys you could have done that before, like just solve for y and then take the derivative, and that's it. That's like the older way we've been doing it before today. That seems a lot easier, right? There's the other option of doing it implicitly. And I'm going to leave you guys to find out dy over dx in just a second. That's going to be your next task. But before it, okay, well, okay. I was definitely never that fast at doing this, but good job. Do you know why there's a plus? Yeah, Ashley. Here, this plus and minus. Oh, that's because I forgot to add in the squared sign. Sorry, guys. That would have probably broken. I would have broken me. Like, what? This is already hard. I don't understand why he did that. This is because I made a mistake. By the way, anytime you watch a video and you're like, "What happened like that?" That's not because I'm reinventing some math that you've. It's just because I made a mistake. Okay, so fair warning. I make a ton of mistakes. Oh yeah, but does anybody recognize why, or why would I make it very explicit that these are two different equations? I'm just saying, find the slope of a circle. That's the equation for a circle. Does anybody remember that from pre-calculus? You take x squared plus y squared, I think, and then like your radius squared is 25. Does anybody remember that? The only problem with this, if I wrote my equation like that, don't write this part down. It's just a little bit of trivia here. There is a test that you need to do to see if you have a technical function. Out of these three functions, or these three things that I graphed, only two of them are actual functions. Why is it that I say that? Or what is the test I use to see if you have a actual function? It's called the vertical line test. Meaning at any point when I draw a vertical line, there should only be one point that it hits. Okay, this green line and this green line hit this linear equation, or this linear graph at one point. It passes. So this is a function. This is the same case. If I do a horizontal line test, it won't pass, but that's not how you do that. That's not how you define a function. You run a bunch of vertical lines to see if it's an actual function. So this is a function. However, this equation that I graphed, x squared plus y squared is equal to 25 technically, which is actually your radius squared. If you remember back to pre-calc, the equation for a circle, that technically is not a passable function. But there's a way that you can work around that. Like I said, if you solve for y, you ended up getting plus or minus the square root of 25 minus x squared. What you're actually doing, I think if I'm doing this right, if you graph y is equal to positive 25 minus x squared, you have a curve that goes like this. Does that pass the vertical line test? Yes or no? It does, right? And then if I graphed a separate graph alongside it or on the same axes, can you imagine what that curve is going to look like? Yeah, it looks exactly the same, but it's a mirror image. I'm sorry. If it was a better circle, it'd be symmetrical. Just pretend it is, okay? It would be another graph. So it would be another curve that points up instead, or opens up. So at this point, to work around this issue, you actually have two separate graphs that you are connecting together to make it look like a full circle, okay? Does that kind of make sense? Sorry, that was not like trivia stuff or trivial stuff, but that's stuff that I think you really should know. Okay, so here's your task. Let's go back to the original task that I was asking you to do. You have two ways to solve for this. You guys want to take a break from the whiteboards, or do you guys want to go back to the whiteboards? You guys want to do it on the paper? Yeah. However you want, paper or whiteboard. Normally I would tell you guys, force you guys to go to the whiteboard. This one you have an option to stay at put, or you can go to the whiteboards. Okay, so solve for dy over dx. You have two ways of doing it. So I'm gonna freeze frame this. You can do it implicitly. You might find it a little easier or harder. I don't know. It's kind of up to you. And then I would suggest at this point, maybe talk to someone to see what they got. So it's a really good way if you're just stuck to see how you're supposed to do this, right? Sometimes I can't explain as well as you guys can explain to each other because I forgot the language of just being a student. I'm a lot more wordy than I used to be. You guys. Oh, you guys even plugged it in too. Oh, you guys did it explicit or implicitly. Very good. Okay. All right. Okay. So it's very deliberate what I did. I did everything in blue for the explicit way to do this. So this is the old school way. I actually didn't even plug in the point yet. Seems like some of you guys did, so that's pretty good. Like you were supposed to do that to solve this problem. But I got this. And between these two problems, I picked this guy. Why did I pick just to differentiate this equation? Y is equal to the square root of negative, or the square root of negative square root of 25 minus x squared. Why did I decide to use the bottom, only this bottom function? Any ideas on why I did that? It has to do with the question I gave you. Yeah, Risa, what do you think?
Is it because the point at which we're finding the slope is in the fourth quadrant?
Yeah, so going back to this, remember how I told you I broke it down that you had two different curves? You had the top curve and the bottom curve. It's really simple. It's not simple. Sorry. That's kind of mean to say it like that. I don't think it is simple. Sorry. At positive 3 comma negative 4 supposedly is a point that's on your curve. So it looks like it's really only on the bottom curve. So I'm going to use y is equal to negative square root of 25 plus x squared. And then I chose to differentiate that explicitly, the older way. I isolate y, then I find the derivative of this. And then supposedly, if I just plugged in my point, whatever x was equal to, which is 3 in the point that I'm looking for, it'd be 3 times the square root of, I think I'm missing a negative here, or am I not? I don't know. 25 minus 3 squared, which is 3 divided by the square root of 25 divided by 9, which is 3 over the square root of 16. And don't worry if you differentiated this explicitly or implicitly. You're going to get the same answer. 3 over 4. I think I am missing a sign. I'm not sure if it was supposed to be 3 or negative 3 over 4. Okay, so why did I bother going through all this? Well, first is to solve the problem, but also I want to show you the benefits of doing it implicitly. Look at the amount of work in blue. Can we agree that there's a lot of room for error in this, like going wrong doing it this way? What do you think are a lot of, like, where do you think people make a lot of mistakes in taking the derivative of this? Like, what things can go wrong? Or what things have I done wrong? Anything that you think is tough in this? Or was this really easy for you guys? Maybe this is really easy for you guys. Well, I got one. Oh, Mr. Wee, I think making the square root to the power of 1/2 is pretty hard. I think that's hard too. Fictional student, or me as a student, okay? I think that's really hard. It's not easy to see it like that. I don't think, taking the power rule of that's very easy. You got to put 1/2 in the front, and then you got to remember the negative sign, and then you got to subtract 1 from 1/2, and you got negative 1/2. I think that's really tough stuff. So another option you can do is to take the derivative implicitly, which I think 1 or 2 groups did, which is very impressive. Just want to make sure I do this right. The other way of doing it is doing this. You just take the derivative right away of the whole thing. X squared plus y squared is equal to the derivative of, technically you got to take the derivative of both sides. It's like basic algebra, but now you're taking the derivative kind of like as an operation. And then this would be 2x, but everything's in terms of x with respect to x. So there's no such thing as 2x squared times dx over dx. Actually, if I did do the chain rule, some people ask me, how come I don't, if I take the if I multiply whatever this is, like, that's going to be 2y, or I'm sorry, that's going to be, take the power of that, that's 2y times dy over dx. How come I didn't take the dx with respect to x, Mr. Wee? Because that's kind of redundant. Actually, what is, if you did do that, you could do the chain rule. You technically take the derivative of x. What is the derivative of just x then as your inside function? The derivative of just x. 1. So you'd be essentially multiplying it by 1. You don't have to do that. I'm sorry. You didn't have to write that. I might have just confused you even more. So I'm sorry. I'm just saying you don't do it to the x, okay? If you're taking it with respect to x, you don't have to take the derivative of x with respect to x. You do need to do it with y, because I told you, I don't know if y is, there's an actual equation within y that is equal to stuff concerning x, okay? What is the derivative of the constant 25?
0.
Yeah. Okay, so now you're left with this guy, 2x squared plus 2y times dy over dx is equal to 0. Then you simply isolate dy over dx. That's the main goal. So minus 2x squared, that's going to be 2y times dy over dx. Then you have 2x squared. How can I get rid of the 2y from this side?
You divide.
And then whatever I do to one side to keep this an equal statement that is true, you must divide the other side by 2y as well. And they both have, both the numerator and denominator have a factor of 2 that can be factored out. So you're left with this, dy over dx is equal to x squared minus x squared, or negative x squared over y. And then how can I answer this problem now? Did I do something wrong here? Oh, I made a mistake. Does anybody see the mistake I made? So this is my common mistake, is the derivative of x squared should have been just 2x to the first power, or if you're writing in pencil, if you're writing in pen, you're going to have to do what I just did, make that into a 1. If you write in pencil, you can erase that entirely. Sorry, this should have been to the power of 1, or just... You guys knew how I knew that I did something wrong? It's because I literally looked over to Gray, and then your face was like, and then I'm like, I must have made a mistake. Yeah, I made a mistake. Okay. But how do I solve the problem now? Yeah, I think this is a lot easier to plug in. You plug in the point, which is a coordinate, which is x comma y. So in place of my x value, I put in 3. In place of my y value, I put in the negative 4, because the dy over dx is literally x, or negative x divided by y. Oh, so I do have to keep that negative sign in the front. I'm sorry. And then you put in the negative 4 on the bottom. I notice that there's 2 negative signs that will cancel out. So my slope at that particular point of this circle is equal to 3 over 4. There are 2 ways you could do this. Implicit is the easier way, but let's say you are stuck not just on your test, but I don't know, for some reason you're having to do this as an engineer, and this function means something else. You're trying to build architecture. You need to find out that coordinate space at 3 comma negative 4, whatever that could mean, the location of a house or whatever it is. And you forget that there's this technique. You could always do it the old way as well. So there is a reason why I showed you both ways. Or let's do it in our context. If you're on your exam and you totally forget how to do it this way, you could still do it the older way as well. Okay? Up to you. Right. Any questions so far? Yes, go ahead, Stephanie.
But what if there's like
X times Y?
Yeah.
you would treat it as like a product, x times y, and you'd have to use the product rule to solve for that. How funny, because we might actually do one like that. Actually, yeah, let's try that. No, let's not. All right, one more problem, and then we're gonna move on to the other section. That's your last problem before we move on to 4-4. Now, please go up to the whiteboards. I don't want you to sit at your desk. 9 o'clock. You got it, Sean? Oh, I'm gonna freeze frame that. Let's see.
We did something wrong.
Yeah. I don't know if that's helping philosophy.
Oops. Okay. Okay. I was writing that. You guys end up getting. Okay. Let's go ahead and check your work here. I'm gonna unfreeze this. I added one more tidbit to your notes. I guess this is from the previous year, because I did go through this similarly last year with last year's class. I wanted you to see that I did make a substitution. Here's the substitution that you might see in your textbook right now that they're already doing. It's not with gamma. It's not with an actual Greek letter, but it's y prime. Okay. It's y prime is equal to dy over dx. So you might see the derivative of y with respect to x written as just y prime. Why is it, though, that I think that dy over dx is superior in this way, in notation? Why do I think that's, in my opinion, the superior notation? Most people would say this is better because it's easier. I totally get that. For speed, this is probably undisputed, not the king, but like better. Queen, leader, right? Okay, I'm sorry. But why is it that I think dy is over dx is superior? It's more clear. In what way is it more clear, though? Dy over dx. What is this telling me more than this? Anybody know? Visibly, what do you see besides the d's? What else did they add in to here that is not seen in when you write y prime?
What's with respect to?
On the bottom, what that means is with respect to which variable. That means dy over dx. It's an equation of y that is variable, that the main variable that we're really looking at, the independent variable that we're actually looking at is x, okay? This doesn't specify what your independent variable is. So in the future, you might see equations where x is not the independent variable. They assign a completely different letter and they call it like g. That makes things a lot more complicated, but that can happen. They could say arbitrary, just why does everything have to be in terms of x? I'll just write in terms of g. Why not? Okay. So all this can be in terms of g, but this lets me know which of those variables is the independent variable. Okay. Anyways, sorry, I digress a lot. Just trying to expand your mathematical horizons. Okay. You should have gone x squared over y. Any questions so far? Okay, we're kind of gonna go at a condensed breakneck speed, condensed lesson for 4-4. Whoops, sorry. Let's go back to my original notes that I was starting on. Go ahead and write this down. 4-4 is the derivatives of exponential. And I'm sorry, that's not crossing it out. That's an attempt to underline the top line, but it didn't go very well. I ended up Xing that out by accident. This should be underlining these words. This line should be underlining these words. 4-4 is derivatives of exponential and logarithmic functions. So I am continuing my notes. Now we're going to start to see more variables anyways. There's a U, there's an A. There's a lot of things going on here. Let me see if I can move this. Oh, that's probably not the way I want. Okay. Let me see what else. So I don't know if I texted you guys last week, but the videos I intended to record last week were already uploaded. So on the website, there are already videos for last week that I didn't go over, stuff I didn't go over that are up on the website. Some of you guys seem to have watched them, but because you guys checked without me telling you guys, which is awesome. It's not easy to do things without like a little helping hand from the teacher, but that's indicative that I'm not really good at updating you guys as frequently as I want to, at least. So check the website frequently on your own to see if there are videos up, because a lot of times I forget to tell you guys, hey, there's new videos up. Okay, For some of you guys, either you guys picked up chain rule today pretty quick, which is very impressive. But maybe most of you guys didn't know what chain rule was, because that was another video I put up last week. Anyways, I'm going to keep going. Sorry. So derivative of natural log of x. So what that's going to look like is d over dx. I'm giving you a bunch of different equations now. A bunch of different formulas for derivatives, because I don't have time to prove these. I don't have time to prove that these things aren't just random facts, but mathematically it does make sense. But you can mathematically prove that the natural log of whatever the exponent is up here. Oh, whoops. I'm sorry. Not the exponent. I wrote that wrong. That shouldn't be an exponent. That's just ln of u. Like you're taking the natural log of u. I'm sorry. A base u, not exponent u. These things are not random, and they were not just arbitrarily made up. They're proven mathematically. There are videos where you can find proofs for these things as well. So that's another one. What time is it right now? Okay, 9:09. The derivative of log base a, or I'm sorry, not log base, log a of base x. That will look like this if you take the derivative with respect to x of log base, not log base a, log base u. That'd be 1 over u times ln of a times du over dx. And one more equation. No, I think that's it. Okay, so those are the four derivatives, four different derivative formulas. I'm sorry, let me go back up. That you're going to have to know for 4-4. My intention is to, I guess at this point, because we only have 5 more minutes of class, is to make a video for an example for each of these derivative formulas, okay? At the same time, I'm going to leave up on those videos a proof for why these work, for why these derivatives are the way they are. Like math proof, like proving that 2 plus 2, whatever plus whatever is always equal to the sum of those two numbers. I don't know. Like, I don't know how else to describe it. That's times a. I know you just jotted this down, but does anybody know why when I took the derivative of, let's say, I'm making these u, and I wrote this as du over dx, why did I choose to write it like that? Because the heading said the derivative of ln of x. But why is it that I all of a sudden changed it to u? Any guesses as to why I'm doing that? Because I'm only asking a question that I think most of you guys, when you guys are doing the work, and you guys are looking at the book, you're like, why did the book say it like this? This is really confusing. Sean? An equation, okay. And why is that important that u could be an equation or something?
The derivative of x is 1, and you don't have to include the right part.
Okay, I guess I would have to show you an example, but let's say I took the derivative of ln of 3x instead of just ln of x, right? Let's say that u is equal to whatever's in there, which is 3x, right? The derivative of this would be 1 over, it says u. What is my u again? But let me ask you, do you remember the chain rule here? Do you also remember, or do you also think that you could take the derivative of just 3x by itself inside there? You can, outside-inside rule, right? So you first take the derivative of the outside, which is literally just 1 divided by whatever is in here. I called it a u, so it's, what is it? It's going to be a 1 over u. That's 1 over u, basically. The reason why we like the notation of u is because it's not always going to be ln of x. It could be the ln of something that you could take the derivative of, an inside function. And in this case, if it's 3x, you can bet your money, yeah, I got to take the derivative of the inside function as well, which is 3. Okay? So this is technically my du over dx. That's what you actually just did. So this is an example. Sorry. Let's kind of make that known that this is an example for this guy here. If I take the derivative, or I'm sorry, if I take the derivative of ln of 3x, I have to make a sign that on the inside it's like ln of u, or I'm going to have to say that that's u, like an inside function. U is equal to 3x. And then how you take the derivative is you take your 1 over u, which is 1 over 3x, and you take the derivative of 3x, the u, or what I assigned as u, which is just 3. I think if you just listen to this auditorily, this is going to be really confusing for you because I just threw out like 5 or 6 different variables in here, okay? So copy this down, study over it, watch the video a few times. I'm definitely going to make another video for this, okay? Otherwise, go ahead and put away your seats and your chairs over there. You guys have a good day, okay? Okay. And most of all, thank you guys for coming to class. Okay.